Podcast is now starting. All attendees are in listen-only mode.
Well, hello, everybody. Welcome to Coffee with Caleffi, August edition. I hope everybody's having a nice summer and making money out there. We've got a really interesting presentation today. Jody, probably a lot of people out there know Jody was most recently with Viessmann before he came over to Caleffi as a technical director there, and he's worked for a lot of other companies in the hydronic industry, so he's got a really solid background with a lot of different components and manufacturers as far as equipment. So the topic today will be on expansion tanks. He's got a lot of expansion tank experience also from a previous employer, so I think this is going to be really interesting. Don't forget to send us questions, and we'll do housekeeping at the end, but stay on board at the end so you can do the questionnaire for us and help us with that. So, Jody, take it away.
Thanks, Bob. For me, this is my first Coffee with Caleffi, and it really was a great topic to start off with. We came up with a list of what we're going to do back in May, so it's kind of been working on a while. And what was interesting is when I started to pull this presentation together, talking with some of the people I know out in the industry, I told them, I'm doing a 1-hour webinar presentation on expansion tanks. And they're like, oh, you're going to be able to talk about it for an hour? As it turns out, I actually had to trim everything down to fit it in, so this is actually going to be a fairly packed hour about expansion tanks. Now, as far as reference materials, as far as hydronics, I was working out of Hydronic number 12, Hydronic Fundamentals. In a couple of areas, we talk about solar expansion tanks, and that comes out of Hydronic number 3. And then also in a couple locations, we talk about expansion tanks and chilled water. That's coming out of Hydronics number 13. Now, from a timeliness, one of the things that I regularly do is, look on the wall and a couple of other of the blog websites to see what people are talking about. And one of the things that I see probably on a regular basis is question about expansion tanks. Because if you look at the industry, there's a lot of expansion tanks out there. There's diaphragm tanks, there's bladder tanks, there's thin, deep drawn construction, there's heavy ASME construction, there's thin expansion tanks, there's fat expansion tanks, there's flat expansion tanks, there's square ones. But in the end, they all perform the same. But from an aspect of what I see for questions, usually when somebody's talking about expansion tanks, the questions that come up are stuff like, why? What is that tank doing? How big of an expansion tank do I need? Is there a problem with going too big? What's the acceptance volume? What's the acceptance factor? A lot of questions about the expansion tank come up. And so today it's really all about trying to pull that together into a single presentation. So let's talk about expansion tanks. Now, one of the things our industry has done very well is trained on the concept of the point of no pressure change. So if I look at what the expansion tank is doing, one of the things it does do is it sets the point of no pressure change. And we're going to talk about this through the presentation. This is really the relationship between the expansion tank and the system circulators. By definition, expansion tank is therefore the expansion of the water in the system. So as I heat up the water expands, the volume becomes bigger. I need to put that water somewhere. As the system cools down, I need water to make up for the contraction. So in the hydronic system, I have water that will enter the tank, be held there, and then move back out as the system temperature changes. When somebody asks me about expansion tanks, I always jump down to the bottom one. A hydronic system should be a closed-loop system. Ultimately, the expansion tank really is there about keeping the relief valve from lifting. I need somewhere to put the expanded water. Now, expansion tanks have been around for a period of time. If you look at what's on the picture here, the original diaphragm expansion tank is the tank that's shown on the left-hand side. It was an original patent by Amtrol 60 years ago. So it's not a new concept with the expansion tank. It came into the market to compete against what's called the compression tank and kind of address some of the issues that the compression tank has. The picture on the right, that's actually out of an Amtrol installation manual from the 60s. So this whole concept of putting the expansion tank in, taking care of the system, has been around for a long period of time. Interesting about time in the 60s, there wasn't a lot of selection and a lot of sizing. When I look at this, this is showing the gentleman there putting up the expansion tank as they said through the manual. With a larger system, it wasn't about sizing the expansion tank. It was how many expansion tanks did I need to put in that system to take care of the expansion. We've grown quite a bit as an industry since then. Now, the question always comes up, expansion tank or compression tank? This is really a discussion of systems. Am I trying to do an air control system or am I trying to do an air elimination system? The compression tank is usually associated with something called air control. We'll get into the details in another slide, but it's a certain philosophy and design of a system. A pre-charged expansion tank is normally associated with air elimination. Let's first look at air control. Okay. So if I do air control, I'm going to do what's called a compression tank. I have a picture on the slide. There's a picture of a typical compression tank off to the left-hand side on the top. You also hear these referred to as plain steel tanks. There's no diaphragm in there. What you have is a plain steel tank with a fitting on the bottom. You see this air control fitting on the right-hand side of the tank, and then there's a gauge glass shown here. Okay? Now, why it's called a compression tank? There is no pre-charge in the tank itself. It's just a steel tank. So when the system is filled, air is captured in this tank, and pressure is generated by compressing the air in the tank itself. The end result is part of the tank's volume is always going to be filled, maintaining the charge on the tank. For instance, if I'm running at 12 psi of pressure, I have to fill that tank up and compress the air by filling the tank up 45%. The other 55% that's left over now becomes my expansion volume. The other big thing about the compression tank and why we're talking, it's referred to as air control, is in that tank there's no separation between the air and the water. So air can be absorbed into the water and it can also be released in the water. So what happens is the air in that tank is constantly migrating into the water and back out of the water. Now, because of that, we cannot design around eliminating the air. It's about controlling the air. So one of the things with an air control system is velocity is key. I have to have enough velocity in my water to entrain the air so that if there's air outside of the tank that's coming out of solution, it can make it back into the boiler. And in this picture on the top on the left-hand side, there's an air control fitting here, and that air control fitting is designed to take those air bubbles and direct them back to the compression tank that's normally installed above the boiler itself. The other thing about these air control systems is there's no automatic air vents. I have to keep the air in the system, otherwise I'll slowly lose the air charge out of the tank. It will waterlog, the release valve will lift, and then I have to recharge the tank itself. Yeah. So this is air control. It's been around before the pre-charge expansion tank. It still exists in existing systems, and once in a while I run across an engineer that's still designing air control. Now, the diaphragm expansion tank. It's associated with the air elimination system. I say diaphragm, it could be bladder. So in this tank, I'm going to have a diaphragm or a bladder that separates the air and water. The first big benefit for me is I don't have to size based on the tank being partially filled with water. Under 12 psi, if my cold static pressure in the system is around 12 psi, typically a pre-charged tank is about half the size of a plain steel tank. Now, by having that separation, it's going to eliminate the air moving from the air side into the water side, so I now can design an air-free system or an air elimination system. In the diagram, I have my air separator with an air vent on the top, and I have high point air vents from the system I get rid of the air problems go away. Additionally, with air elimination, since I'm not as concerned with entraining the air bubbles constantly in the system to bring them back to the air control device on top of the boiler, I now have much more freedom in my flow velocity throughout the system. Mark, any questions yet?
Not yet, Jody.
All right, we'll continue on. Or again, as questions come up, please present the questions, and we'll cover them as we make our way through. Now, when it comes to expansion tanks, they usually are one of two separate designs, either a diaphragm tank or a bladder tank. We'll first look at the diaphragm tank. Now, typically, I would say probably the bulk of what we see on the residential side is primarily diaphragm tanks. If I look at this cutaway that was provided by Angel, it's showing here's my tank, and then the black here is a flexible diaphragm. Okay? So the diaphragm sits in there. When there's no water, the diaphragm is up against the top of the tank. As water comes in, it goes in between the tank and the diaphragm, and then it inverts the diaphragm and flexes into the tank itself and holds the water. Now, design-wise, with a diaphragm tank, a lot of times the question comes up because of design, should I be concerned with that diaphragm stretching? If the tank is properly sized for the application, the diaphragm simply inverts, and then when the system cools down, it returns to its original shape to push the expanded water back into the system, but there's no stretching, so the stretching really doesn't play into the life cycle of the diaphragm expansion tank. Now, the other option is the bladder expansion tank. Instead of having a flexible diaphragm, it has a flexible bladder that sits down into the tank, water connection on the flangeway here, so the water's going down into the bladder, the air surrounds the bladder in the tank. So with this, it works very similar to the diaphragm tank. The water comes into the bladder, but now rather than flexing the diaphragm, it's either expanding the bladder out to its original shape or being pushed back in by the air charge in operation. Now the bladder tanks, you'll often see listed as either a full acceptance bladder or a partial acceptance bladder. This really describes the relationship between the volume of the bladder and the volume of the tank. So if I have a tank that's a full acceptance bladder, let's say it's a 500-gallon tank, the volume of the bladder is also 500 gallons. Yeah. Whereas a partial acceptance tank, the bladder is some volume less than the full volume of the tank. So I may have a partial acceptance tank that the tank's volume is 500 gallons, but the bladder volume may only be 200 gallons. Why the two different types? From an application standpoint, there's virtually no application where I'm going to have to use the full volume of the bladder itself. From an acceptance point, usually most installs, I may be using maybe 30, could be 40% of the bladder's volume, probably much less. So if I can go with a partial acceptance bladder, there's less bladder in the tank. There's also less money. The cost of the tank is less because I'm not paying for that full acceptance bladder. Now, we talk about the acceptance volume of the bladder of the tank. Now, the other thing that we have to talk about from a definition standpoint is what's called acceptance volume. Okay? Now, acceptance volume really is a function of the expansion tank itself. The system. Where I design a hydronic system, I have a certain volume, I have a certain temperature range. That's going to mean that the water expands to a certain point. So when I look at tank sizing, I have to make sure that the tank can take the acceptance volume. or the volume of water that's going to be generated by that expansion. For instance, okay, this is an water expansion factor chart. So off of this chart, if I look at various minimum water temperatures and various maximum water temperatures. So for my example, let's say I'm heating the water from 50 degrees Fahrenheit to 180 degrees Fahrenheit. Each gallon of water through that temperature change is going to expand 0.0275 gallons. So, for instance, if I had a 100-gallon system, I have 2.75 gallons of water that I now need the expansion tank to hold. Okay. So this becomes one of the criteria we start looking at the expansion tank sizing. This is an important information that's needed to pick the right size tank. Now, something that manufacturers do print. I would say pretty much everybody has it somewhere in their literature. They'll have what's called the max acceptance volume. So, for instance, this is off of Amtrol's website. This is their AX series tank, their diaphragm tanks. So this max acceptance volume column here, that represents the volume that if I fully invert that diaphragm, how much water I can support or hold in that diaphragm. And from the aspect of system design, since I don't want that diaphragm to stretch, when I select the tank has to make sure that it will accept that volume. So for instance, I look at this AX20, its acceptance volume is 2.4 gallons. I have 2.75, so I may have to look at the AX40 as my tank choice. I want the max acceptance volume to always be more than the acceptance volume that's going into the system through expansion. Are there any questions?
A couple of questions, Jody. Is there any downside for someone selecting an expansion tank that is oversized?
Oversizing is an excellent question. We'll actually see this when we start to get into the sizing process. But from a sizing, if I'm doing a commercial system, typically I'm going to do what's called a critical sizing. I'm going to try and find the right expansion tank that gives me the best combination of volume and performance. Now, to get there, I may have the system go all the way up almost to the relief valve pressure. If I go large in my expansion tank, what's going to happen is it's going to flatten out the pressure fluctuations. So I may design for a maximum pressure on my system when the system's hot of, let's call it 25, 26 PSI. If I change my expansion tank size, I go large on the expansion tank, the 26 PSI may only be 17 or 18. So the real answer is other than the added cost of the tank and possibly taking up a little bit more room in the mechanical space, I don't really see any downside of going larger with the expansion tank. Mark, do you have another question?
Another question is in regards to the type of expansion tank with a bladder. I think we'll save it towards the end since you're far into the material. Mm-hmm.
So, if I do need to size the expansion tank, there's 5 pieces of information that I need. I need to know the minimum system pressure and the maximum system pressure. I need to know the minimum system temperature and the maximum system temperature. And then I need to know the system water volume. All of these play a part in selecting the right size expansion tank. Now, for the minimum pressure, I have to start somewhere. Okay? This is a table that talks about positive pressure to prevent boiling. We also need positive pressure on the top of the system for air vents to be positive acting. Typical hydronic design normally looks at 5 pounds of positive pressure at the top of the system. It'll let me, with a safety factor, I can get up to 210 degrees and not worry about the water boiling. Additionally, if I am looking at air vents, 5 psi is going to give that air vent enough positive pressure that it will act properly and won't weep. Okay? Now, if I'm looking at other systems that possibly may be operating to higher temperatures, I may have to increase on the positive pressure at the top of the system. For instance, if I do solar, I probably will be running at a higher positive pressure. Actually, I got that on. I'm going to leave that to a little bit later in the presentation. Okay. So, what is my minimum pressure? First, I'm going to go with my 5 psi positive pressure at the top of the system. Then I have to figure out the static pressure of the system. I measure from the location of the expansion tank and the fill valve how many feet is the top of my hydronic system above there. Then I'm going to take that number of feet, multiply it by 0.433, and that will calculate the static pressure of the system. I then will add that 5 pounds of positive pressure to it, and that will be the pre-charge on my expansion tank and the fill pressure on my fill valve. Typical two-house, normally we're in the neighborhood of about 12 psi. That's why expansion tanks come pre-charged to 12 psi, and fill valve pressure is also set to 12 psi. That also means that if I'm going to do a heating system in a 3-story house, I'm probably going to have to increase the static pressure of my system, increase the pre-charge of my expansion tank, increase the fill pressure on my fill valve. As I kind of alluded to on the previous slide, this relationship in thermal solar does change. If I'm doing a pressurized closed-loop solar system, I typically will run at a much higher positive pressure. Depending on the manufacturer, it may be as much as 20 psi because we have to suppress the boiling at some of the higher temperatures that you may see in thermal solar systems. So our first piece of data is the minimum pressure. That's how we're going to get there. Next, I need a maximum pressure. The maximum pressure is based on keeping the relief valve from lifting. So typical residential application, I have a 30-pound relief valve. Now, I don't want to push that pressure all the way up to 30 pounds. Most of the relief valves tend to start leaking before they get to the actual fully open pressure. So that happens usually at about 5% away from the design pressure. To keep the relief valve seated, most people will design 10% less. So for a standard residential heating system, the expectation is I'll probably push the pressure up, possibly up to 27 psi to give me good expansion range, but I want to stay below 27 to make sure the relief valve doesn't lift. So now I have the information for my pressure side. Minimum pressure is going to be 12 psi. Maximum pressure is going to be 27. Okay. Now, why we need that change in pressure? It's about accommodating air in the tank. I am going to compress the air, but because of something called Boyle's law, and that's actually that P1V1 equals P2V2 in the center of the screen, that's an interpretation of Boyle's law. As I compress the air, the pressure in the tank on the air side has to go up. Okay? So when we start to look at system design, this is why with an expansion tank, I can't fill that tank all up with water. There's always going to be a portion of the tank that's water and the portion of the tank that's air. And this equation actually determines how much water I can put into it, and it's really based on the pressure range the tank's going to be cycling through. So if I go to some charts, acceptance factor charts, for instance, if I say minimum pressure is going to be 12 psi and the maximum is going to be 27, I look on here and I come with an acceptance factor of 0.36. So at 12 psi, the tank is full of air. At 27 psi, the tank is 36% of that tank is holding water, 64% of it is holding air. Okay? And this is not a factor of tank size. This is a consistent factor based on the pressure swing of the tank itself. Now, with this, important point to remember is the pressure in your system will change with temperature. Now, so everybody's like, I've heard it before, what's the expansion tank doing? I've heard people, either say or post somewhere, well, it's holding the pressure on the system constant. Based on the size of the expansion tank, that pressure is going to change as the temperature changes. It may start at 12. It might get up somewhere in the 24, 26 range. It might only top at the 18 or 19. But as that water expands, you will find the pressure in the system changing. Questions about that?
Yeah, I think that's a good question. So when you refer to the point that an expansion tank connects into a system as the point of no pressure, it's important to delineate that's with pumps from a pumping standpoint. Is that correct?
Yes, that's correct. In any hydronic system, there's a lot of different relationships that are going on. The point of no pressure change really is the description of the relationship to the expansion tank to the system pumps or circulators. That truly is the point of no pressure change, and in a few slides we're going to cover that. But from the relationship between expansion of the system water in the expansion tank, the pressure has to go up because I have that air charge that I'm working against, and if I'm going to reduce the volume of the air charge, the pressure has to go up. So I will see the pressure change, but it's really the temperature, the relationship of change in temperature, and it's independent of pump operation.
Very good.
Okay. So I have my pressures, which will tell me what percentage of the tank's volume I can use storing the expanded water. Now I have to look at how much water, expanded water, does it need to hold. So it's back to that chart we looked before, and again, minimum system temperature here, maximum system temperature here. So if I'm going for a total hands-off system that I'm filling it and not draining anything, so 50 degree minimum temperature, 180 degree maximum temperature, there's that 0.0275 acceptance factor. Again, if I have 100 gallons of water, the tank has to hold 2.75 gallons. And again, that 2.75 gallons is just the water component. If I was going through to do a calculation, I'm trying to stay away from calculations today, but if I was doing the calculation, that 2.75 gallons represents 36% of the total tank volume. So I'd have to work the calculation to get the total tank volume. Now, I'm actually today going to take the simpler route. There's a lot of great resources out there for tank sizing. TACO has a software package where I can go through, enter the exact information that we talked about, and come up with a tank size. Okay. Here's one from Amtrol. Bell & Gossett has one. I believe Wessels has one. So there's a lot of great resources out there to size the expansion tanks without having to actually go through doing the calculations longhand. And these charts, these software packages all have the information that we pretty much have been discussing so far. I need a total system volume, minimum operating temperature, a maximum operating temperature. We're going to talk in the future about the effects of glycol, but I also have to tell it what percentage of glycol is in there, and then a minimum operating pressure and a maximum operating pressure.
Jody,
everybody, yes.
Just a quick clarification. When you're talking pressure, you're talking gauge pressure, not absolute pressure, correct?
That is correct. That's a very good point. These are all gauge pressures.
Okay. And then as it relates to determining the minimum operating temperature, you're showing an example on this Amtrol spreadsheet of 70. That could be, depends on your installation, that could be 50, it could be 40, something less than that. You could be in a chilled water application and cooler yet. Is that correct?
Yes. Yeah, it's the minimum operating temperature could be in a wide variety of numbers, and it really comes down to where, the lower I push that temperature from the sizing, the larger the tank is going to become. A lot of times I've seen, and again, this is going, back a few years when I was doing expansion tank sizing. A lot of times I would see guys revert, and why I went to 70 degrees. A lot of times guys have reverted to that temperature rather than going to something lower, because when you filled the system, when you've purged it, when you've heated up, when you've gotten rid of all the air, from after that first cycling of the system, depending on whether the mechanical room is heated or not, a lot of times the system never drops back down below with a hydronic heating system below that 70-degree number. So I did used to see a lot of guys use that. That's kind of why I went probably with that number on the screen itself. But yeah, that number could be a lot lower, particularly when doing chilled water. It's probably going to be down around 40, 45, depending on what the design chilled water temperature is.
Very good.
And on the bottom here, it will give you a tank recommendation. Now, residentially, most contractors, most of our the wholesale partners we have out there, really don't go through the full size. Okay, this is an example of a chart which most of the manufacturers have. That's a quick sizing method. You enter in it on the vertical column with the type of radiation, and then you go with the net output on the boiler. So, for instance, if I'm doing baseboard radiation and I have a boiler that has a net output of 100,000 BTUs, I want to do a Model 30 expansion tank. This is based on incoming pressure of 12 psi, a 30-pound relief valve, and a 200-degree average water temperature. It's very conservative. So this kind of chart here has been used for a long period of time, and really, you don't see people running into too many expansion tank sizing problems. But they look at that chart and say, well, geez, why aren't there any problems? Well, I'm going to start off with the temperature. For a 200-degree average temperature, you're running your high limit up around 210 degrees to get there. So if I'm running at a lower temperature, there's less expansion, the tank starts to become oversized. I've actually sat down and worked the numbers back. If I'm going from 12 to 27 psi, and I am running between 50 to 200 degrees Fahrenheit as my average system temperatures, low and high, and a Model 30 Extra is good up to around 45 gallons of system volume. So you look at that, and that gives you a lot of leeway in system design and not having to worry about pushing up to the maximum limit of that tank. If I'm putting this in a system, modern system, condensing boiler, low water content, maybe 15 to 20 gallons of total water in the system. This is why a lot of these expansion tanks, I'm saying I'm sizing for 27 psi. In reality, the high pressure, when the water reaches this high temperature is topping out at I'm probably topping out at maybe 17 or 18. It's because this chart is very conservative.
Hey, Jody, if I could add one thing in here. I know there's a lot of guys, one of the websites that I hang out on is guys that do wood and pellet boilers, and oftentimes they'll have a lot of storage capacity with them, sometimes hundreds, sometimes thousands of gallons. Some guys got 1,000, 2,000 gallon LP tanks in for storage. So something like that, you got to be careful when you have that kind of volume that you really want to crunch the numbers, because this, with 100,000 BTU boiler and 1,000 gallons of system capacity, this obviously wouldn't work. And the other thing I would say to that, guys say, well, I'm not going to buy a big expensive compression or a bladder type of tank for that, and they try to use just plain steel compression tanks, and be aware that sizing can be, 75, 80% bigger on a plain steel tank where you don't have a captive air bubble in there. So sometimes you do want to run the numbers if you're doing stuff out of the typical, residential volume type of system. So that's where you have all the information.
Oh, absolutely. Even, if you look at this here, back to your point, if somebody's doing any kind of buffer tank, with that buffer tank, whether it's 60 gallons, 75 gallons, or 119 gallons, definitely shouldn't work off of the chart. I would go back and do a calculation off of one of the design software off of one of the manufacturer's websites, because you're certainly above that 45.7 gallon total volume size.
I discovered that one of the websites I went to, one of the manufacturers, when you size, especially for a large system like that, it'll give you the compression tank size as well as a diaphragm or bladder tank size. And the example I did for a customer that was doing 2,000 gallon worth of water, it went from like 150 gallon bladder type tank to 383 gallons of just a plain steel compression tank. So it's a huge difference. So just be aware of that.
Yeah, and the other thing with the compression tanks, the first thing everybody all of a sudden recognizes when they go from a pre-pressurized expansion tank to a compression tank, the first thing that really catches everybody's eyes is the size increase on the tank. But then the second thing that has to also be recognized as an added cost on installation is I have to support that tank, and that tank's going to be at least half full of water. So you have a lot of weight that you're supporting somewhere in the building, whether you're building some sort of saddle for it or trying to support from the joist of the floor above.
Good point.
Yeah. So, questions about sizing?
Yes, Jody, a question came in concerning sizing. So, when does the need for an ASME expansion tank come into play as it relates to sizing?
Well, from the ASME, really, from the sizing process, the tanks, whether they're ASME or non-ASME, they're sized properly. I'm going to go with the cop-out answer of ASME is required when an engineer specifies it. It's right now I can't remember all the nuances of ASME specification, but it's written in there about public access, and I think volume plays as well. But unfortunately, that's something that I don't readily have the answer for at the tip of my tongue.
Okay, very good, thanks.
Yeah. Now, kind of talked a little bit about this in bits and pieces, and the decision of where I'm going to put it into the system. The point of no pressure change is one of those topics that has been well discussed within our industry, probably over the past 15 to 20 years. So when I'm putting that expansion tank in there, I have to look at the relationship between the expansion tank and the pumps in the system. I choose a pump or a circulator. The pump generates, based on its pump curve, it will generate a certain amount of differential pressure and flow rate depending on the losses through the system. Now, it doesn't increase pressure or decrease pressure. It generates a delta P or differential pressure, and that's tied to its point of no pressure change. So I put the expansion tank on the suction side of the pump. In this drawing here, for instance, this is 12 psi here. That's my static pressure, my minimum pressure on the system. Now, with the expansion tank on the suction side, the pump's head pressure, or its delta P, is additive above the static pressure of the system. Okay? Does a couple of things for me. First off, it's going to ensure that my system always sees, as a minimum, the static pressure of the system, something that I've calculated and I want to see. So I'm not going to run into any kind of pressure problems. In fact, the head pressure, with the exception of getting close to the inlet of that pump, the head pressure, in fact, is going to be additive all the way around to the static pressure of the system. So it's actually going to give me a little bit more margin, safety margin, on the limits of my system. The other thing it does, all circulators, pumps, they all need a minimum suction pressure on the inlet of the pump. By putting the expansion tank on the suction side of the pump, it locks it in at the static pressure of the system and ensures I'm going to have proper inlet suction pressure. End result is cavitation is not an issue. If I put the expansion tank on the discharge side of the pump would still generate the same differential pressure, or delta P, that it would if it's in the exact same system. But now the discharge pressure of that pump is locked in to the static pressure of the system. If it's going to generate its delta P or differential pressure, the only way it can do it, the suction pressure drops. So a couple of things happen. First off, I've decided 12 psi in this is my minimum static pressure on the system. With that being locked in at the suction side of the pump, now the dynamic losses take place, and as I move around my hydronic system loop, my pressure starts to decrease and drop down below that 12 psi pressure point until I get around to the side of the inlet side of the pump, where I'm now at the full delta P or differential of that pump. The other thing that happens, the pump suction pressure drops based on the delta P of the differential pressure of that pump. I may all of a sudden get into a cavitation problem because I've now dropped my suction pressure down below the minimum design suction pressure for that pump there. So from the design side, what we like to see is something like these two drawings out of Hydronic 12. Figure 4-7 in the upper left-hand corner, direct connected boiler to system. So here's my boiler, here's my expansion tank, here's my circulator. Point of no pressure change is locked in here. This circulator or this pump's head pressure is additive over that static pressure, and I have a nice performing system. The other nice thing about this, it's now air elimination. I put my air eliminator in that exact same location. When it's this gives me that point of low solubility, I get rid of the air. My system is now air free. Now, in figure 6.8, now we're looking at a condensing boiler with a smaller mass to it. So I'm going to go into it as a primary-secondary connection with my hydraulic separator. Again, here's my hydraulic separator. All circulators are pumping away from that hydraulic separator. Now, you'll notice that my expansion tank is actually tied in on this drawing all the way to the end of my low-loss common piping. If I am sizing that header pipe properly, there's very little pressure drop across it, and I like to use this picture because it gives me design freedom. I can put it on the end of this header pipe here, or I could place it anywhere around my hydraulic separator, anywhere I need that expansion tank from a room type standpoint. But by doing this way here, all of the pumps in the system are pumping away from the point of no pressure change. All of the head pressures are additive. The system will perform better. Couple of example pictures. I really, love this boiler room. I wish every boiler room was this neat and clean and had this much space in it. So this is a boiler room with 4 boilers over onto the right-hand side of the picture. Here's my hydraulic separator here. Here is my expansion tank. I follow the pipe down and around. Expansion tank's tied in here. My 2 system circulators are pumping away from the point of no pressure change. Each boiler has its own circulator pumping into the boiler. They're pumping away from that point of no pressure change as well. Again, same thing on this picture here. I'm going to kind of jump through this one a little bit quick to pick up a little time. And, another one here. Here's my pump. Here's my expansion tank tied in here, suction side of the pump. Okay. But again, each one of these installation examples, we're pumping away from that expansion tank, adding the head pressure of the pump to the static pressure of the system. Questions about insulation?
Yes, a quick question. Can a small expansion tank be installed above the pipe, and will the diaphragm eventually fill with air and decrease the acceptance capacity of that expansion tank?
The question is, can the expansion tank, Mark, everybody hears the question, correct?
Yes.
Okay. Yeah, question is, so you're talking about putting an expansion tank above the pipe and placing it upside down. Okay?
Yes.
Now, normally with an expansion tank, that diaphragm is pushed right up against the edge of the tank until the system pressure gets higher than the precharge on the tank. So normally there's no space for that air to get into. I've seen plenty of installations where the tank is sitting upside down. In fact, the original boiler in my house here, the expansion tank was off of a tee, off the top of the boiler, teed off on the same little manifold piece that had the expansion tank and the release valve on the top of it. Now, you're probably not going to get air trapped in there because when you may purge at a higher pressure, but when you bring the system back down to the operating pressure, that diaphragm goes flat and pushes the water so that there's nothing trapped inside there. The other thing that works in our advantage is solubility. I bring water, my system, as I'm moving the water around the system, my air eliminator is separating. I'm separating the air bubbles, bringing the air bubbles up, so I'm reaching a point of low solubility. The expansion tank is uninsulated, so the water in the expansion tank will cool down over time. As it cools down, the water picks up the ability to absorb more air. So if I had a little pocket of air in there, eventually over time that pocket of air will absorb in the water, and then as the system contracts, when that water moves out of the expansion tank, it carries it back out again. So I guess from the aspect of the question, there's really no issue putting it upside down in the system on top of the pipe. You know, the air shouldn't get trapped in there, and if any air does, eventually it'll work its way out.
Very good.
Let's talk about antifreeze, polypropylene glycol. I pulled up a chart. This one's looking at a 40% polypropylene glycol mixture. I'm going under the same conditions that I pulled up on some of the old charts so we can compare the two. So if I'm looking at initial temperature of 50 degrees Fahrenheit and a final temperature of 180, that polypropylene glycol, that 40% glycol mix, is expanding at the rate of 0.0495. Let's go to my 100-gallon system. So it kind of gets it to a number that I find is a lot easier to get my hands around. A 100-gallon system, changing temperature from 50 to 180, at 180 at 4.95 gallons of expanded water glycol mix. How does that compare with straight water? From a previous calculation, I know that my acceptance volume, straight water, is 2.75. Glycol expands significantly more than water. And the other thing to remember is that expansion rate changes in its concentration. So when you're sizing for glycol, it has to be accounted. If you're doing your calculation through one of the sizing software packages, whether it's Antro or it's Pecos, it's Wessels, it's B&G, one of the things that they ask you for, and about halfway down the screen, is the antifreeze glycol. What's the percentage? It makes the adjustment for that percentage. So if I'm looking at this system here, 200 gallons total volume, 70 to 180, 50% glycol, minimum pressure 12, maximum pressure 30. These are on the bottom of the recommended tank models are based on the glycol, the expansion of glycol. If I compare that to water alone, I'm doing an AX40. Glycol, I'm jumping up to an AX60. So doing an LBC series, I start out at a 50 with water, I'm up to a 130 with glycol. The reason the L series didn't change from a 200L, that's the smallest L series tank they offer. So that's why that one didn't change. But from the aspect of system design, glycol has to be accounted for because of the much higher expansion rate than water. Now, another thing that has to be considered, and I've seen this a couple of times on the wall, people start to talk about operating pressure, and they say, well, you know what? I typically don't run my systems at 12 psi. I run them at 18 or I run them at 20. There has to be a little bit of a concern on how that it changes the dynamics of the expansion tank. Okay. Because if I go from 12 psi to 27, you look at that number there, I will be using 36% of that tank's volume holding the expanded water. If I go from 20 to 27, that 36% drops down. I'm going to round up to 17%. So one of the concerns is if you're going to run at a higher pressure, you just beware that you are running at a reduced acceptance factor. You're going to be able to use less of that tank's volume storing that water. So, typically at a higher pressure, the tank's volume has to get larger. The other thing that always concerns me when I listen to these discussions is when they're going from 12 psi to 18 or 20, are they adjusting the precharge, or are they just bumping the pressure up by increasing water, putting more water in the system? The water goes in, it goes into the tank, and it compresses the air. Something that you should be aware of if you're doing it that way is if to compress the air in the tank by bringing water in rather than just doing it with air, when I take that tank from 12 to 20 psi, I've just lost 23% of the tank volume is now holding air, holding water, because I've had to decrease the air volume by 23% to compress it up to 20 psi. Yeah. So the point here is, if you're going to run at a higher pressure, make sure the tank is sized for that higher pressure. Otherwise you may run into issues where the tank that was was sized properly at 12 psi, all of a sudden is going to be too small when I get up around 20. There are a couple final things before we go to the final questions, and then I'll turn it over to Bob. We need to touch a little bit on solar. Okay, solar, a closed-loop pressurized solar system, will require an expansion tank. Couple of things that are different in the setup and the sizing of the tank. First off, we're going with solar. We're going to run, as I said earlier, going to run at a much higher positive pressure to ensure that we suppress boiling in the collector itself. So some solar panels, stagnation, 325, 375, 4 1/4. I'm going to run at a higher positive pressure to take care of that. Now, something else that comes up in various manufacturers' installation and setup manuals is something called a safety seal. The solar collector is outside the building envelope. So the water in the collector has the ability to contract as outside temperature drops. So if I fill the system up and it's a 60-degree day, and during that night it drops down to 30 degrees, that water in that collector is going to contract as the temperature goes down. If I have a little bit of water, most manufacturers that are looking for this safety seal will say to pre-charge the tank to the static pressure and then fill the system 2 to 3 psi higher. You'll have a little bit of water sitting on top of the diaphragm in that expansion tank that I then can let the system use to keep the pressure on the system when the fluid in the collector contracts. Now, the final thing that also increases the size of the expansion tank in thermal solar applications is the fact that most manufacturers will also look at the tank being large enough to accept the volume of the collector if the collector stagnates and the solar fluid does boil. So now I look at our solar panels, they hold anywhere to a gallon to a gallon and a half of fluid per panel. So if I look at the sizing procedure, which is a long formula in Hydronic 3, part of the sizing process is to size the fluid of the collector, and that becomes the baseline of the sizing of the expansion tank. Then there's chilled water. Chilled water tanks tend to run a little bit smaller. They don't see the high temperature difference that a hydronic heating system does see. Now, with this, everything is calculated based on the chilled water temperature as your minimum temperature and the minimum pressure at that point. Now, when we start to fill the system up, the system is probably going to be filled at a higher temperature than the minimum on the system. So, on fill with chilled water, one of the things that has to be calculated is when I'm filling the system based on the temperature, how much extra water do I need to put into the expansion tank so that when the system drops down to its operating temperature, I don't lose pressure. Could be, if I have a way of metering it, it's probably going to be done by adding additional volume of water. If I'm not metering the fill, I may have to do it based on calculating a final pressure. Now, the final part of this is maintenance. Expansion tank manufacturers recommend that the pressure is checked on an annual basis. Why? The tanks can lose pressure. First place is the Schrader valve on the top of the tank for setting the pre-charge and making adjustments. Tanks come with a cap for the Schrader valve. Use the cap. The cap is actually the seal. If I don't have a cap on there, the tank will lose air as it leaks by that Schrader valve. It's not the most airtight seal that you'll see out there. Okay? Now, the other place that the tank can lose pressure is directly through the diaphragm. Just as oxygen can diffuse through PEX tubing, You know, depending on the blend of the diaphragm, the thickness of the diaphragm, and how it's cured, the air, particularly the oxygen part of air, has the ability to readily diffuse through that diaphragm, so you will see a bit of it passing through the diaphragm itself into the system. Most manufacturers will tell you that on average expansion tanks probably lose a half a pound of pressure on an annual basis. You know, so it does have to be checked and it does have to be adjusted. Now, before I turn the presentation over to Bob, are there any final questions?
Jody, this is Mark. We have a gazillion questions. I'm trying to keep up with them. Do you have time for more, or do you want to wait till Bob?
Well, I just right now, what are we? We're almost on the hour, so if people don't mind us going a couple minutes over, we'll work through some of the questions before turning it over to Bob, I guess.
Okay. Well, a couple questions then. One in regards to ASME. It's not a question, but we had at least 3 responses of the criteria used for whether or not an ASME tank is needed for an expansion tank. One criteria says that if the total volume of your expansion tank is greater than 119, much like other types of tanks, an ASME rated tank is needed. Another engineer wrote that if your system pressure or your PRV is rated over 30 psi, then that will require the expansion tank to be ASME. And another one just came in that the tank needs to be rated 2.5 times the working pressure of the boiler. I guess that's what they do in Bronco territory. I guess that means Colorado. So there's different regional requirements for ASME, I guess. So your point's well taken. It's whatever the engineer understands is the needs in his marketplace. Another quick question, though, concerning tank sizing. Can you parallel expansion tanks? If you need 100 gallons of acceptance volume, can you parallel, 425s, and does the math work the same?
The answer is yes. Yeah. With expansion tanks, the big thing is I have to make sure that they're all pre-charged to the exact same pressure, and my preference is to manifold them together and then bring them into the system to a single point location. Yeah. This way here you have one. My concern is I want to have one point of no pressure change. So I match the pre-charge. They're all going to fill and they're going to draw down at the same rate, and then through the manifolding and coming into the single point, they'll operate like a single expansion tank. Very good. And 2 more questions that were related to that. When you do pre-charge them, do you pre-charge them, just to clarify, to the static fill pressure? Is that correct? You pre-charge them to the static fill pressure. That's correct. And thanks for, you just reminded me, when you check the pre-charge, you have to make sure that there's no water on the backside of the diaphragm. Otherwise, you won't be reading pre-charge pressure. You will be reading system pressure. So the pressure across that diaphragm equalizes. If my system is at 18 psi, I check the pre-charge on the tank. The tank's going to show 18 psi as well. Okay, very good. Thank you. I have a few more questions if we have time at the end, and otherwise I'll let you pass it on to Bob. Yeah, I think we'll pass it on, Bob. Make sure we get our housekeeping done.
Yeah, well, thanks for everything. If I could add one thing, too, probably the best thing is when you take it out of the box, check the pre-charge there, because I know some of the solar tanks that we've sent out had really high pre-charge pressure to them. So if you assume it's 30 pounds or 20 pounds, just don't always assume that the writing on the side is accurate. So check when you take them out. So yeah, what do you got for housekeeping here? And we've got the new Caleffi Excellence program coming on.
Well, the All-Star lineup first.
Okay. Looks like my slide's a couple seconds behind. There it is. Okay, I got it. Yeah, so that's what's coming up next for our Coffee with Caleffi's. It looks like I'm back in September. Kind of what you do when you start up for the first time in the fall, a little pre-check and some of the things that are new and unique with new boilers that we'll go over. And then Kevin from our office here is going to talk about product certification, all the different things like low lead certifications, ASME, different things like that. I'll be back in November. We're going to do a live lab demo. We've got a really nice lab that we've been putting together here all summer up in Milwaukee. We're going to set up a camera here and show you some demos there. That'll be pretty exciting, kind of a hands-on thing. Always a crowd pleaser. Siggy's going to be back for 2 in a row. That'll be December January too, analyzing. It has to do with pumps, selecting pumps. So how do you analyze what pumps needed in the system, and also for troubleshooting, you're going to replace a pump. Did the last guy put the right pump? And so those will be really popular in those. So that's what's coming up. And of course, we always ask you for ideas for next year. We want to get our list together for next year. So if there's something, I know that we get a lot of input on that. And that's why we got to the expansion tanks. We had a lot of people requested this, so this was the by request presentation also. So thanks for sending those in. And then what else here? Oh yeah, so at the very end, before you log out, if you will, please, there is a little survey. We're asking you some questions about balancing valves. We're trying to learn some more about some products that we want to offer in the balancing market. So if you have time, stay on for that. And that's also where you request a certificate of participation now. For some reason you get kicked out and you don't get to that, we are going to get you the certificate. If you send us an email, if you missed the questions at the end, we'll get that to you. But participate in that, and also if you could. Thank you. And then I think the last one is, of course, all our social media stuff out there.
Your computer must be running a little bit on the slower side.
Yeah. That's out now. It was mailed out last week, so we've got Hydronic 15. That's going to be another good one. We just consolidated our hydraulic separation again into a newer issue, so that's out. Look for that. If you don't have it, let us know, and we'll make sure you get back on the mailing list. And I think the last one was probably the Caleffi Excellence Program.
Yep, that's why it's showing up now on my screen.
Okay, all right, yeah. We are changing up the program a little bit for the Caleffi Excellence. It's going to start up again in September, and what we're going to do basically is you're going to vote. Everybody that comes to the Coffee with Caleffi has a chance to vote for the winners, and we'll pick 3 winners a month. Every one of those winners will instantly get the iPad mini, so it's kind of an instant gratification thing, and instead of having to wait for the end of the quarter. So that's going to be a little bit, I think that's what people requested. Can you do that? So we did that, and then, of course, the grand prize winner will be picked from those. We'll get you, the attendees, to pick the final 3, and then we'll, with the staff here and some industry experts, we'll pick the grand prize winner to go on the trip to Italy for that. So, and of course, there's one of our previous winners from up in Montana. And yeah, I keep in touch with a lot of different ways. We tweet, we're on Facebook, we got a bunch of YouTubes. We're going to add some more today. In fact, I'm up in Milwaukee. We're going to film some more tech tips and some more YouTube videos while I'm up here. So we'd love to hear from you. And if there's nothing else, I think I'd like to thank everybody again, and we'll see you in the next one.
Hey, Bob.
Now, Mark, I guess if there's questions that are left over, if anybody wants to stick around, if you want to go through them for them, we can do that as well.
Let's do that. We lost about 30 guys, so we still got the 100 that are still on. So a few more. You showed a photograph of an expansion tank connected by way of a pretty decent-sized run of pipe. Does the length of that pipe between the expansion tank and the system affect that tank's performance any? And does that pipe factor into sizing significantly?
Most of your tank manufacturers will, based on the run of the pipe and the size of the tank, make a recommendation. The thing is, you're looking at you don't have a very high flow rate through there. We're talking for a 100-gallon system, a little bit over 2 gallons that are moving, and it's a slow process as the water expands. So the pipe size does matter, but I'd say in most cases it's going to be maybe 1/2 inch to maybe 3/4 inch, but the tank manufacturers will also list that in their literature of what that pipe size should be. As far as performance, like for instance for the point of no pressure change, it's really where the tank is connecting into the piping system, not physically where the tank is located.
So basically the expansion tank doesn't know what size pipe connects it to the system, performs identically.
Yeah, as far as the tank is going to perform identically. It's just that particularly when I get to very large systems, I don't want to go with a small pipe because there will be a certain amount of friction loss in there. So I want to open the pipe up so there's not much pressure drop between the connection into the system and physically where the tank is sitting.
Very good. Another question concerning the different types of expansion type tanks. There's a diaphragm tank and a bladder type tank. Do you see any difference in performance between those two, if sized correctly?
Performance-wise, a diaphragm and a bladder tank will perform the same as long as they're sized properly. What it really comes down to, part of the reason why there's 2 types of tanks is really, let's go with manufacturability and cost. are probably two of the biggest reasons for the two styles of tanks. The other thing that typically drives bladder tanks on the commercial side is the ability to replace the bladder without replacing the tank. You know, because you're looking at some fairly substantial size steel tanks. You know, it may be the tank is actually larger than the access into the room itself. So a lot of times you'll see bladder tanks, replaceable bladder tanks specified in commercial jobs so that there's a certain level of repairability, if you will. Diaphragm tanks, they fail, you have to replace them. But from a performance standpoint, they perform exactly the same from an operational standpoint.
Okay, very good. Jumping over to compression-type tanks, you reviewed that early in the webinar.
Yes.
There's the issue of the air absorbing into the system and then coming back out of solution as the system cools. Is there any method for separating the water from the air, like a film or oil that is used to prevent that migration of air back into the system, or is that something that's not common or capable of being done?
I don't know of it being done, you know, because then the concern is what happens, well, somewhere along the line, if I put that, well, I guess there's no fitting to place that in there. And the concern also is if for some reason I end up draining that tank down, where does that oil go? You know, so it really becomes, I live with the limitations of the compression tank, or I move over to an air elimination system with a pre-pressurized tank.
Got it. Back to diaphragm-type tanks, and I'm not sure if you addressed it, I had to step out, but as it relates to the quality of the air that a tank is filled with,
yes.
Is there any issues, best practices as it relates to the type of air and the quality of air?
That actually, the air side of thing really varies from manufacturer to manufacturer. I mean, I've seen, reading through some of the manuals, I've seen it say where you can adjust the pre-charge with a bicycle pump on one extreme, and on the other extreme, they recommend that you charge the tank with either nitrogen or air that's been dried through a desiccant tower. Okay? It really comes down to the drying of the air. You know, what they're looking at is removing moisture. It's probably one of the big things. You know, I fill the system. I add a charge into the tank with moist air. I have oxygen and I have water vapor. So if the location where the tank is located, if I drop down below the dew point of that air charge in the tank, all of a sudden I now have water forming on the inner steel surface of the tank with oxygen, and I can get a certain level of corrosion within the tank itself. That's why some manufacturers will call for either dry air or nitrogen. But other manufacturers say pump it up with a bicycle pump. So it really is all over the place.
Okay. Okay, thank you. Jody, there's a number of questions that are probably more application specific that you can address afterwards, so I'll pass this back over to you and Bob the wrap.
Oh, excellent. Well, thank you all for coming, and I guess I'm going to be signing out.
All right. Thanks, everybody.